Let's now do some examples of some past examination relativity questions. One thing I do need to point out though is that if you're looking at examinations earlier than 2016, there was a very different relativity course then, and they had lots of other things that are no longer part of the course. Or for one specific example, there's something where the physics understanding has actually changed slightly. So just be really careful in past questions that you're doing for these. This one's still relevant though. We've got two spaceships, delightfully called Discovery and Enterprise. They're both travelling relative to an inertial frame of reference at 0.8 c in the same direction. We are told the spaceship Discovery shines a light beam forwards towards the Enterprise as shown. So I think we are another observer. We are in our own inertial frame of reference, and we measure the velocity of each of these to be 0.8 c. So that's 80% of the speed of light. The relative velocity between them is 0 because they're not moving further apart from each other or closer together. The question asks, what is the speed of the light beam according to the captain on the spaceship Enterprise? Now this question, I thought they were going to, when I was reading it, before I actually got to what the question was asking, I was thinking they were going to ask us what the observer in the inertial frame of reference would have noticed. But it doesn't actually matter. Anyone who measures the speed of light, doesn't matter whether they're on the Discovery, they're on the Enterprise, or they're this other person that, from their perspective, Discovery and Enterprise are both going at 0.8 times the speed of light past them, everyone is going to measure the speed of light to be c. No greater or no less when we're in a vacuum. So the next questions are from 2012 examination. I think it's examination 1, back when they had 2. It says, which of the following factors affect the speed of light? I want you to have a read of these options. Hopefully you can see that B and C immediately need to be wrong. They're suggesting that if we have an observer that's travelling relative to someone else, or someone who's emitting a light and an observer is looking at them, that's going to affect the speed of light. As we've looked at with Einstein's postulates, the speed of light does not depend on the speed of the observer or the speed of the source. So B and C immediately need to be wrong. You might then gravitate towards D, thinking speed of light never changes. Well, this is an incomplete sentence. The speed of light never changes in a vacuum. If we put that in the statement, that would be absolutely correct. Speed of light never changes when we're within a vacuum alone. The problem is when light starts traveling into different media, for example, if we weren't in a vacuum, we were in air, or if instead of air we were in water or glass or diamond, the speed of light changes significantly. And that's got to do with the properties of the medium through which the light is traveling. Now they refer to it as electrical properties here. We're going to be referring to something called the refractive index in a future topic. So A is the answer for this one. Before I move on, I just want to indicate how powerful it is to read a question carefully and check if there's any nuance here. 72% of people in this particular year group actually got the wrong answer here because they were used to just thinking speed of light never changes, speed of light never changes. However, it's really important to notice what the question is actually asking, and remember you're choosing the best option possible. D did look like the best option until we realised it didn't mention specifically in a vacuum. So that's a really good question to look at the examiner's comments for. Okay, take a read of this question. Pause if you need to. So from this question, we can see the stationary player has measured the speed of sound to be 335 meters per second. And when they say stationary, they mean stationary with respect to the ground, and the alarm is also stationary, so the alarm's not moving around here. Now with this alarm, the sound waves propagate out from the source. Oh, excellent circles me. Now the problem is, if we have a player running away from the alarm, that sound is going to have to travel further because as the sound travels from here to here, this person has travelled up a little bit. So the sound needs to catch up with this player. So this player is going to measure a slower speed of sound. And that's got to do with our relative velocities here, with someone travelling in the same direction as the sound, so the sound appeared to be slower. Very different for the player running towards the alarm. they are going to be running through more of those sound waves. So it's going to appear that that sound, because it's running towards where the sound is propagating out from, it's going to appear that the sound is actually traveling faster. So we need to look at this. Well, let's make a note there. Faster. I'm going to put measured speed of sound for both of these, because they're measuring it from their own inertial reference frames. Now remember, this question's trying to trick you. Option A is trying to see if you know the difference between light and sound. Like we just looked at in the previous question, this one here, the speed of light is the same for all observers, but that's not true for sound. Sound is going to behave how we would expect classically, so that means we're anticipating that relative motion here. So slower speed of sound for the player running away from the alarm, faster for the person running towards. So let's be a little more specific here. When we say a slower measured speed of sound, the person running away from the alarm is traveling at 5 meters per second. So that means sound is going to appear to be 5 meters per second slower. So that means the speed of sound measured by this person is only going to be 330 meters per second. Oops, I circled the wrong one when I looked at this the first time. I think I mixed up my slow and fast. The person running towards the sound is going to measure a speed of sound to be 340 meters per second. Does that agree? Oh, good. So we've definitely checked. We could have answered D here just based on our understanding of the first one, but we double checked it, checking the person traveling towards the sound as well. Okay, still on this exam, let's look at this one. We're told about a quasar, which is a distant star, is visible to amateur astronomers. Have a read of the data that we're given here. So it says, which of the following is the best statement about light from the quasar? We're going to use the process of elimination to determine this question, because you'll see why in a moment. So first option, light from the quasar will be traveling slower than 3 by 10 to the 8, and option B is light will be traveling faster than 3 by 10 to the 8, the standard speed of light. We immediately know that these two options have got to be wrong. The speed of light in a vacuum is always going to be observed to be 3 by 10 to the 8, so we can't have faster or slower. Now, we're with option C or D, and it says the light from the quasar has taken blah years to reach Earth, or option D, light from the quasar has not yet had time to reach Earth. The way we are able to see things is the process of light hitting our eyes and then all of the fun biology stuff that happens from there. To be able to see something, we need to have received the light. So option D cannot be the right answer. It needs to have had enough time to be able to get to Earth, because we're specifically told this star is visible to amateur astronomers. Well, astronomers generally, it's visible to someone on Earth. So that light must have reached Earth already. We're going to learn the strategy to be able to calculate that time in a future lesson, so don't worry, you don't always need to use process of elimination. One of Einstein's postulates is about inertial reference frames, and it's the fact that the laws of physics are the same in all inertial reference frames. If you're not familiar with that term, inertial reference frame, you need to go back and watch the previous video or ask me. It says, which of the following best describes the properties of an inertial reference frame? A, its movement is consistent with the general expansion of the universe. That's got nothing to do with an inertial reference frame, so we can get rid of it. B, no observer in the frame can detect any acceleration. Well, that sounds relevant, yes. An inertial reference frame is one that is traveling at constant velocity, so I'm thinking that this might be the right answer. So let's double check the other ones. C, it is traveling at speeds much less than c. No, we can have an inertial reference frame traveling at 0.999 c, so long as it's traveling at constant velocity. Not true. And D, it's traveling in a straight line. This is almost the right answer. If we were traveling in a straight line at a constant velocity, that would be fine, but they haven't specified that. So yep, B is our best answer here. Let's move on to some 2013 exam questions. So question 1, again, this is in the detailed study. We've got James is stationary on a footpath. Okay, there's James. Amanda drives past at a constant speed. Yes, for some reason we stand up in cars now. So it says, which of the following statements is correct? So we're going to be looking at a lot of incorrect statements here. A, Amanda is in a non-inertial reference frame because she's moving relative to James. No, as we previously spoke about, inertial reference frames merely depend on someone traveling at a constant velocity. Now, they have said on a footpath while Amanda drives past at a constant speed of 60 kilometers an hour. They haven't specified that she's turning a corner. So for the context of this question, we can assume that it's constant velocity, although I would have liked that if they had narrowed down that it was definitely traveling in a straight line. So not A. B. James must be in a non-inertial reference frame because he's stationary at the moment. Nope. A stationary reference frame, or at least stationary with respect to the ground, that is perfectly fine. That's a constant velocity of 0. James is not stationary in his reference frame because he's moving in Amanda's reference frame. Also not true. In James's reference frame, he's stationary. He looks at his feet, he doesn't see them moving. He looks at Amanda, sees her moving. From Amanda's reference frame, she is stationary in hers. I like to think with reference frames, you're the center of the universe and everything's moving around you. So in Amanda's reference frame, she's stationary and James is moving. So C doesn't make sense. James is stationary in his reference frame. The fact that Amanda sees him moving in hers doesn't change what he observes from his reference frame. So we're really hoping that D is going to be the answer here. Amanda is stationary in her reference frame even though she's moving in James's reference frame. Absolutely. In our own reference frame, we're stationary. We, again, are the center of the universe and everything is moving around us. Really nice example of this is if you're sitting in a train, you are stationary in your reference frame and you see everything outside flying by, even though if there was someone in a reference frame outside of the train, they'd see you moving. So, Amanda's stationary in her reference frame, yep, even though she's moving in James's. What she looks like in James's reference frame has nothing to do with her reference frame. I said reference frame one too many times then. It's a bit of a tongue twister. Okay, question 4. We've got the spaceship Andromeda. That's the name of our nearest galaxy, Andromeda. I might be saying that wrong. Is traveling at 0.7 C towards an asteroid series, and we've got A and C here nicely. It sends a light pulse to a nearby ship, Bradbury, which is approaching the asteroid from the far side at 0.8 C. So it appears like this 0.7 C and 0.8 C is with respect to series reference frame. The speed of the light pulse measured by each body is always going to be the speed of light. So the answer for this one must be D. Because we're in a vacuum, the speed of light will always be C. So that means A, the person at A, the person at B, and the person at C will always measure the speed of light to be the speed of light, lowercase c. Okay, 2014 questions now. First one is talking about the concept of an inertial frame. It's used widely in what we're talking about at the moment. Which of the following statements best describes an inertial frame? Remember, an inertial frame, that's a frame of reference that's traveling at constant velocity and all of the laws of physics normally obey. And it says best describes, so there might be one or two of those sort of like, oh, that's kind of right, but not quite kind of things. So, A, frame in which relativistic effects do not occur. That's got nothing to do with inertial reference frames. Within an inertial reference frame, as I said, all it depends on it traveling at a constant velocity and all of the normal laws of physics are going to apply. So if I were to throw a ball within an inertial reference frame, I would observe projectile motion like I would be expecting. If I was in a non-inertial reference frame, I'd see some weird things happening with that. Maybe the ball not traveling in a parabola as I would be expecting because I'd be accelerating somehow. So part B, a frame in which Newton's first law of physics is always obeyed. Well, that's true. Is that going to be the best answer? Let's see with the other answers that we've got here. A frame in which all time measurements result in proper time. Well, that's not true. Proper time we're going to be exploring in more depth a little later on. And proper time is something that, if we're looking at an event, the proper time of that event is the time measured in a reference frame that's stationary with respect to that event. So, for example, going back to when I was talking about dropping something, doing a projectile motion experiment, just say I was in some sort of spaceship, which looks like a goldfish. So this person here, they're throwing a ball, they're doing an experiment to see what happens. Proper time would be measured in that spaceship. Even if this person was traveling along at 0.8 C, I'm looking at an event that's happening in that spaceship, so proper time would be happening there. The problem is, if there was someone who was in another inertial reference frame and they wanted to do an experiment here, so they decided to throw a ball, I could not then measure the proper time of that ball. I am no longer stationary with respect to that event. As I mentioned, I would be whizzing by, so I cannot measure the proper time of that event because I am not stationary with respect to that event. Frame in which all time measurements are proper time. No. If I was measuring something inside of my spaceship, yep, that's proper time. But if I'm measuring something outside of the spaceship where it's no longer in my reference frame, it's moving with respect to my reference frame, no, doesn't work. So, last one, a frame whose acceleration is small compared to g. Well, whose acceleration is small compared to g. That wording is kind of annoying because the acceleration is 0 and one would say 0 is small compared to g, but it's not the best answer we've got here. B is the best answer. It's talking about the laws of physics being obeyed. D implies that it's got a non-zero acceleration. Again, I can see why you might argue that you might think that that's the correct answer, but it's not the best answer that we've got here. B is better. Pause and have a read of this next question here. We've got 2 spacecraft. And people inside them, Ajax and Hector. So, it says a radio signal is emitted by Ajax towards Hector. The navigator Hector, now this question is kind of annoying, but I still wanted to give it to you, uses a classical understanding of radio waves travelling at a speed relative to a medium fixed with respect to the galaxy. So what that means is... I guess it doesn't say measured to be here, it's expected to be. So Hector unfortunately doesn't understand relativity, and he doesn't understand that light always travels in a vacuum at the speed of c, speed of light, 3 by 10 to the 8 meters per second. I'm waffling. So this person Hector would be expecting a slightly different speed. So what would that speed be? A strange thing to understand is that classical physics sees light as needing to travel through a medium. And that medium was previously known as the ether. If you're interested in learning more about this, definitely look up the Michelson-Morley experiment. Wonderful thing, which showed absolutely zero result. One of the best examples of that in physics. Huge paradigm shift. So, let's model light, instead of light traveling through a vacuum, let's model it as little droplets creating ripples in water. The ripples being like the light and water being like the ether, the medium through which light was believed to travel. If Ajax was emitting the light, he's just putting a drop into that water. So the speed of Ajax himself doesn't matter. If he puts a drop into that water, that droplet is going to create ripples spreading out there. And those ripples are going to travel at the, in quotation marks, speed of light anticipated in this medium. So it's a little complicated, but we are assuming that the speed of light is unaffected by Ajax's speed in this example, because he's just released a droplet of water to create those ripples. The speed of that ripple itself is unaffected by him. A light wave is coming out of Ajax there. So that light is travelling at c according to this frame of reference, and Hector is anticipating that he's going to be finding a slower speed of light, or measuring one. Imagine, for example, you're on a highway and you've got a car, you're travelling along at a particular speed, and you've got a car, I don't know why the car's longer, travelling past you quicker. They don't appear to be flying past you like they would appear to someone who is stationary on the road watching you both go past. If someone was travelling, just say you were travelling at 90 kilometres an hour and someone was travelling at 100 kilometres an hour, you're travelling in the same direction, the relative speed of that other person compared to your reference frame would be 10 kilometres an hour. It's the difference in the speeds when you're travelling in the same direction. So, Hector will see the light travelling more slowly, and it means that it's going to see the light travelling at c minus 0.4, which would be 0.6c. This is similar to how we did our calculations for sound. With sound, we're not going super fast speeds, so we can ignore any relativistic effects. They're so small we wouldn't be able to actually measure them, really. Well, it depends on your measuring device. Cool, so we're on to a 2017 exam here. Student sits inside a windowless box that's been placed on a smooth riding train carriage. He conducts a series of motion experiments to investigate frames of reference. So when it says smooth riding train carriage, I think we can assume a few things here. It's not speeding up or slowing down. We wouldn't be having a smooth ride there because we'd be jolted forward or backwards, as you probably experienced on our trains. We're not experiencing any bumping up or down, and we wouldn't be turning any corners because we would be shoved either left or right on the train. So I think we can assume the smooth riding train carriage is trying to tell us that we're in an inertial reference frame. So it says, which of the following observations is correct? The results when the train accelerates are identical to the results when the train is at rest. No. If the train accelerated, we're no longer in an inertial reference frame, so we're not going to see the same results for physics experiments we'd expect when we're just doing something on the ground, for example. The results when the train accelerates differ from the results when the train is in uniform motion in a straight line. Oh good, we didn't even need to make this assumption here. I'm glad that they've specified a little later on, but it was handy to have that in our minds earlier. So it looks like it's B. Let's check the others. Results when the train is at rest differ from the results when the train is in uniform motion in a straight line. No, both of those are inertial reference frames, so the results would be completely identical. You would not be able to tell if you were in a train that was traveling at a constant velocity in a completely smooth track, if there were no windows. You wouldn't be able to tell if you were moving using under those circumstances I just outlined, or if you were stationary. That kind of weirds my brain out a little bit. So C is incorrect. The results when the train accelerates are identical to the results when the train... Oh my gosh, no. Not an inertial reference frame. Not true. So B's got to be our answer here. Get it? Got to be our answer. Okay, we're in the 2018 exam now. Yanni is stationary in a spaceship traveling at constant speed. Does this mean that the spaceship must be an inertial frame of reference? We need to justify our answer. So a few things here. We need to demonstrate that we know constant speed is different, well, not necessarily the same as constant velocity. Constant speed could be something traveling in a circle, but that is accelerating. So we need to be very, very clear about that. Okay, we're making it abundantly clear here. Constant speed does not equal constant velocity, as Yanni or Jenny could be changing direction. An example could be traveling in circular motion at a constant speed. So some sort of acknowledgement of the fact that you know that constant speed is not the same as constant velocity. Then answering the question, therefore not an inertial reference frame. So a nice justification there, and clearly stating that it's not an inertial reference frame. Okay, I'm getting terrible flashbacks to this question. It says, what is the second postulate of Einstein's theory of special relativity regarding the speed of light? Explain how the second postulate differs from the concept of the speed of light in classical physics. So this is a 3-mark question, and I'll give you a hint, only 9% of people got 3 marks for this question. So I know that we can definitely be up there if we're really, really careful, and we're mindful of the mark scheme here. So first off, statement of Einstein's postulates are directly in the study design, so we need to make that clear. Let's note it down. Okay, so the postulate that relates to the speed of light is the speed of light has a constant value for all observers. If you wanted to be extra thorough and you were nervous, it would be good to say for all observers regardless of their motion or the motion of the source. So please write that down if you need to. It says, we need to relate this to classical physics. And in classical physics, they do not think, well, I say they, classical physics models light as not being a constant thing. So for example, if the source and the observer were approaching each other, the speed of light would appear faster than 3 by 10 to the 8. And if the source and the observer were moving apart from each other, the speed would appear to be a bit slower than 3 by 10 to the 8, dependent on those speeds. It's not just enough to say the speed of light would change. You need to be, or say the speed of light is not constant. You needed to provide more detail here, and these were difficult marks to earn. So let's note down something like that. So, building into our point, classical physics anticipates, or use another word, differing values of the speed of light when there is relative motion between the source and the observer. So I think this would earn us 2 marks, but we need to be abundantly clear. What if the two things were moving towards each other? What if they were moving further apart, like I mentioned previously? So let's note that down. Okay, so I've said if the source and the observer are getting closer, the light speed appears to be greater than 3 by 10 to the 8 meters per second. And I've just put in brackets just to cover my bases. Slower if the source and the observer are getting further apart. Really demonstrated we know exactly what would be anticipated with classical physics here. So have a look at these questions now, see how you go, let me know if you have any queries. Thank you.